Welcome AP Chemistry students to Unit 7 Equilibrium, probably one of the more important units in AP Chemistry. So equilibrium is the fact that when a reaction happens and produces some product, products oftentimes will collide with one another and return to reactants. Only a handful of reactions are one directional. I know that you learned that in first year chem that reactants form products, and we briefly touched on equilibrium. However, in this unit we are going to focus largely on the concept that reactions can travel in both directions. So equilibrium by definition is when the rate of the forward reaction is the same as the rate of the reverse reaction, right? Like for example, when you're on a treadmill, you need to run forward at the same rate that the treadmill runs back. That keeps you in a state of equilibrium. You stay in one place even though you are in constant motion. Equilibrium is dynamic, meaning it is constantly a give and take between the reactants and products. We symbolize equilibrium with a double arrow between our reactants and products. To get you to understand this, we watched the TED Ed video about equilibrium. And the point here where it talks about how the rate of the forward reaction eventually equaling the rate of the reverse reaction, that level playing field between the two is the state of equilibrium. Now the video showed that as they were equal concentrations, that is exceedingly rare. Most of the time, the concentration of your reactants and products will be vastly different from one another at equilibrium, but you know you've reached equilibrium when there's no change in the concentration of reactants or products. So notice that in this graph, we've reached equilibrium when both lines have flattened out because they're no longer changing. Now that does not mean that no molecules of C and D are colliding to form A or B, or that no molecules of A or B are colliding to form C or D. It simply means that from a macro standpoint, from us looking into our beaker, that the concentrations are constant. So we can discuss the ratio of reactants to products with what's known as an equilibrium constant. For any given reaction at a specific temperature, when the reaction reaches equilibrium, there's some ratio of reactants to products, which is what the video alludes to here. What is the ratio of reactants to products when they reach equilibrium? Half and half? Sometimes, but as exceedingly rare. Most of the time, it favors one side or another. And we can only determine that by looking into our beaker and doing some calculations. So in order to calculate the ratio of reactants to products, we calculate what's known as the equilibrium constant, or the mass action expression, or the equilibrium position. It's given lots of different names, but it all boils down to is the variable K. Uppercase K, it is different than the lowercase rate constant K. Equilibrium constants oftentimes have a subscript. So sometimes they'll be called the equation equilibrium constant, KEQ, or the solubility constant for if we're dealing with a soluble salt, or if we're dealing with gases, we might have a K for different pressures. But it all boils down to the ratio of products to reactants. And if we know that ratio of products to reactants, we can determine some things about the reaction. So if K is a large number, something like bigger than 1, that means that the reaction favored products, because since K is larger than 1, we had to have a large number of products and very few reactants. So the reaction heavily favors the formation of products. However, if K is a small number, something less than 1, that means we had very few products and lots of reactants once we reached equilibrium, meaning the reaction favors the reactants staying reactants. And as I said, there are lots of different K values. KEQ is what we will most often talk about, or what we're going to start talking about, the equilibrium constant for the equation, or Kc, the equilibrium constant based on concentration. At the end of this unit, we'll talk about solubility. In the next 2 units, we'll talk about Ka and Kb, which deal with weak acid and weak base equilibrium. Kp is explicitly used when dealing with pressures, so explicitly dealing with gases. They all denote the same thing. Every single one of them is the ratio of products to reactants. It's simply a matter of what are those products and what are the reactants that determine if you're dealing with an acid or a base or pressure. That's what these different subtext denote. So calculating our equilibrium constant is fairly straightforward. You simply take the concentration of your products over the concentration of your reactants. But we pay attention to the stoichiometric coefficients. So the stoichiometric coefficients become exponents of that specific species. So for the general reaction, A plus B gives us C and D. It's C and D raised to their coefficients over A and B raised to their coefficients. Now the example problem here is based on concentration. So this is an equilibrium constant based on concentration. If we were dealing with all gases pressure, the pressure of a gas is proportional to concentration. So as concentration of a gas increases, its pressure increases as well. So Kp is simply to take the partial pressures of a specific gas raised to its stoichiometric coefficient times the partial pressures. That is literally the only difference with Kc and Kp that you need to worry about right now. When dealing with equilibrium constants, there are some things to keep in mind. When we talk about equilibrium, we are trying to talk about a change in the concentration of our reactants or products. So if something is massively concentrated, chances are its concentration is not going to change. So for this reason, when we write equilibrium constants, we do not include solids or liquids. If something is denoted as being a solid or a pure liquid, you exclude it from your equilibrium concentration. The reason for this is because something like, say, water. If you have a reaction that includes pure liquid water, water has a density of 1 gram for every milliliter. So let's say that you take a reaction, you carry it out in 100 milliliters of water. If 100 milliliters of water are in your reaction, that means you have 100 grams. 100 grams of water would be about 5.5 moles of water. 100 divided by 18 is 5.5. And at 100 milliliters, or 0.1 liters, that means your water's concentration is 55 molar. And 55 molar is massively concentrated. It's not going to change in one direction or another when we carry out a reaction. It might change by 0.1, but what is 0.1 out of 55? It's negligible. So when we talk about equilibrium, we're looking at changes in concentration as the reaction occurs. And if something is massively concentrated, its concentration, for example, if water were on this graph, started at 55 molar, and if the reaction went on, when it reached equilibrium, it probably was at 55.3 molar. Did it make a sizable difference? No. So for that reason, when we talk about equilibrium, we outright ignore pure solids and liquids. So here we have the reaction between ammonia and oxygen to make nitric oxide and water. Write the equilibrium expression. So equilibrium expression is just the ratio of products to reactants raised to their coefficients. So our products here are nitric oxide raised to the 4th times water raised to the 6th over ammonia raised to the 4th times oxygen raised to the 7th. Professor, you just made a huge thing about how we don't include water. Yes, I did, Sunshine, but I was talking about liquid pure water. This is vapor. This is water vapor. It's a gas. So we do include gases because a change in the concentration of a gas will have a massive difference in terms of the pressure. So here is our equilibrium expression for this reaction at a given temperature. Sometimes you'll see equilibrium expressions with a subnote of what that temperature is because temperature will shift a reaction and therefore will shift the value of K to favor endo or exothermic reactions, but that is a story for later. If we were asked to write the Kp for the above expression, it's almost exactly the same. The only difference is instead of brackets, we'll use P and parentheses. So the partial pressure of nitric oxide raised to the 4th times the partial pressure of water raised to the 6th over the partial pressure of ammonia to the 4th times the partial pressure of oxygen to the 7th. If we're not given an equation, we have to write an equation and balance it. So solid phosphorus pentachloride decomposes into liquid phosphorus trichloride and chlorine gas. And again, this is an equilibrium because chlorine gas and phosphorus trichloride could collide to produce solid phosphorus pentachloride. Balancing, this reaction is balanced because 1 phosphorus makes 1 phosphorus, 5 chlorines makes 3 plus 2 is 5 chlorine. So the reaction's balanced as is. I don't have to do anything. When I go to write the equilibrium expression for this reaction, it's the products, chlorine gas raised to the 1st times phosphorus trichloride raised to the 1st. However, phosphorus trichloride is a pure liquid, so it's not included, over phosphorus pentachloride raised to the 1st, but phosphorus pentachloride is a pure liquid, so it's not there. So it's simply the equilibrium expression for this reaction is the concentration of chlorine gas to the 1st. So at equilibrium, whatever the concentration of chlorine gas is, that's our equilibrium constant. To write Kp, it's the same process since we know that it's simply the concentration of chlorine gas as our only value. Kp would simply be the partial pressure of chlorine gas raised to the 1st. Copper 2 sulfate pentahydrate. Pentahydrate means that we are dealing with a hydrate. So penta is 5 waters. So this is a dot water. Is heated and drives off the water vapor to form solid copper 2 sulfate. So the water vapor is released. We are dealing with a hydrate. It is a solid and it produces a gas. Balancing wise, 1 copper sulfate makes 1 copper sulfate, but 5 waters have to evolve out. Once again, to write our equilibrium expression, it's going to be the concentration of our products over the concentration of our reactants raised to their stoichiometric coefficients. However, we take out any solids or pure liquids. Copper 2 sulfate pentahydrate is a solid and therefore not part of our reaction and therefore not part of our equilibrium expression. So is copper 2 sulfate, the product. So once again, our Kc for this reaction is simply the concentration of water vapor raised to the 5th. Kp is going to be much along the same lines, where it's the partial pressure of our water vapor raised to the fifth. So on page 14, you will see practice on doing equilibrium expression. As for various different types of K, don't get thrown off. The only one that's going to look or be different is anytime you see Kp. When you see Kp, please use P's instead of brackets. Any other time, use brackets. Please pause the video and do the left side of page 14. Now, in the previous unit, we talked about Hess's law, and before that, we talked about mechanisms. For mechanisms or Hess's law, if we are dealing with a reaction that has multiple steps, and we know the K expression or the K value for all of those steps, we can determine the equilibrium constant for the overall reaction, because it's simply the summation of the steps. So the equilibrium constant for a sum of reactions would simply be to multiply the values of K. If we for some reason need to reverse our reaction, the inverse of K, or the reciprocal of K, would be the equilibrium expression, right? Because equilibrium expression is products over reactants. If the reaction swaps, wouldn't the values just swap? For everything else, it's pretty straightforward. If we double a reaction, simply square K, because doubling the reaction would double those coefficients. It would effectively take, if I double the reaction, I double those coefficients and end up with the same value. If I were to triple the reaction, cube the value of K. So here we have the Haber process, what allows humanity to bypass Earth's carrying capacity, nitrogen and hydrogen producing ammonia gas. We're given the values at equilibrium for 127 degrees Celsius. So we are asked to determine the value of K at 127 degrees, which again, remember, is important because it will be different if we change the temperature. So the value of K would simply be to take the concentration of ammonia at equilibrium and square it, then divide it by the concentration of nitrogen gas times the concentration of hydrogen gas cubed. So we'll just plug those values in. 3.1 times 10 to the minus second squared over 8.5 times 10 to the minus first times 3.1 times 10 to the minus third, to give us an equilibrium constant value of 37,950. Now you might be saying, Professor, but what are the units? Well, equilibrium expression is a ratio of concentrations. Concentration squared over concentration to the fourth. We don't provide units for equilibrium expression because they're always in concentrations and they're very awkward. So we don't use units. Equilibrium concentration is a naked number, meaning it's just a value. It is a magnitude to allow you to say this reaction heavily favors the formation of products because this value is way bigger than 1. Now for question B, we have the same temperature, but the reaction has been reversed. So the reverse reaction would have an equilibrium expression like this. And since the equilibrium concentrations are constant, the values that those variables represent are constant. Rather than calculate it again, I can simply take the reciprocal of K. So if I take my answer to the -1, or put 1 over K, I get that the reverse reaction's equilibrium constant is 2.64 times 10 to the minus 5th, meaning that in the reverse at this temperature, the formation of reactants is favored, because this value is so much less than 1. We have way more reactants at equilibrium than we do products. For letter C, they halved the reaction. Now again, we could calculate the value of K by writing our equilibrium expression. However, that's way more work than we really need to do. We could just simply take K and raise it to the half. Or if you're mathematically inclined, you might know that when you raise something to the half, you're really taking the square root of it. So on my calculator, if I simply hit square root of 37,000, I get that half the reaction at 127 degrees Celsius would have an equilibrium constant 195. Exercise 3 has us figure out the equilibrium constant for a reaction given its possible mechanisms. So we have to treat this a lot like Hess's law, right? Hess's law, again, is when we took a reaction and tried to get it to match up with the overall reaction we were going for. So to start with, I need chlorine monofluoride, which only appears in reaction A. So I'll use reaction A, and chlorine monofluoride is a reactant in reaction A. So I'll take reaction A however, I need half of reaction A to end up with 1 chlorine monofluoride. So if I take half of reaction A, that means the value of K for reaction A, I'll raise to the half. Now with that out of the way, what's my next reactant I need? That's right, fluorine gas. Fluorine gas appears in reaction B. So for reaction B, fluorine gas and oxygen produce 2 oxygen difluorides. And the value of K is a negative 1.4. Bit of a typo there. There's no such thing as a negative value of K. So 1.4 is the value of K for reaction B. That's what happens when you steal a problem that's not yours. Alright, for reaction B, I only need 1 fluorine gas. So again, I'm going to half reaction B. So the value of K, I'll take the square root of. Lastly, I need chlorine trifluoride as a product. So I need reaction C flipped. And of reaction C, I actually only need half of reaction C. So for reaction C, the value of K, I'm going to put 1 over it, and I'm going to take the square root of that value. Now, if everything was done correctly, everything will cancel out that I don't need. 1 oxygen cancels out 1 oxygen. 1.5 oxygen difluorides cancels out 3/2 oxygen difluorides, and half a dichlorine monofluoroxide cancels half a chlorine monoxide, giving me chlorine fluoride plus fluorine gas gives me chlorine trifluoride. Now the value of K is simply going to be the product of all of these values. The square root of 2.3 times the square root of 1.4 times the square root of 1 over 3.8. So the value of K for this reaction, given the mechanism we just looked at, would be 0.92. So this reaction favors reactants. We have more reactants at equilibrium than we do products. Now Kp and Kc are proportional to one another, but they aren't exactly the same because concentration and pressure of gases are not exactly the same. However, we can use a derivative of the ideal gas law to determine the value of our equilibrium constant by pressure if we know the equilibrium constant by concentration, or vice versa. So it uses the ideal gas constant, the temperature in Kelvin, and we simply raise that to the change in moles. The change in moles is the product's number of moles of product minus the number of moles of reactant. Specifically, the number of moles of gas product minus number of moles of reactant gas. Simply taken from the stoichiometric coefficients. I sometimes refer to this as the politically correct formula. It is no longer on the AP exam. It is not on your formula sheet. And when you take your quiz, please remind me to give it to you, because it's not on your formula sheet. You're not expected to memorize anything for this course. So Kp equals Kc times RT raised to the change in N. Let's practice by doing. So we are given a gas equilibrium. We're asked to find Kp. Kp would be to simply take the partial pressures of our products over the partial pressures of our reactants. So a little bit of plug and chug. And we get the value of Kp at 25 degrees is 1920. We can use that value to determine the equilibrium constant in terms of Kc. So Kp and Kc are related by our politically correct formula, where Kp equals Kc times RT raised to change in moles of gas. In order to get Kc by itself, I'll divide by RT to the N on both sides. The formula we'll use is that Kc equals Kp over RT to the change in moles. Kp we already have, so 1920 over RT. We need our ideal gas constant, so we'll use 0.08206 since it is the one we use when dealing with gases which have pressures. All of our pressures here are in atmospheres, all the more reason that we will use 0.08206 as our value of R. Our value of temperature is in Kelvin, so 25 degrees plus 273 will give us our Kelvin temperature, which is 298. So that expression we are going to raise to the change in moles. Our reactants contain 3 moles. Our products contain 2 moles. It's products minus reactants. So our change in moles is a -1. And with all of that in place, we are ready to roll. 1920 divided by gives us a Kc value of 46,950. So with that being said, you are able to finish page 14 in your packet. For number 3 and 4, both reactions occur at 25 degrees Celsius or 298 Kelvin. Please use 298 to finish number 3 and 4. I will see you next time when we talk about how to determine equilibrium when you are given starting values. I will see you then.